All right, welcome to UAB Data Science Club number 32. Today we're going to be talking about deep learning, and we're going to be using another one of the Kaggle Learn courses to do that. Last week we talked about convolutions and what that looks like, and so today we're going to talk about the next step is what you do with those convolutions. It may not look super connected right now because from what I can tell, this tutorial is more like how to program using TensorFlow and Keras a little bit, and TensorFlow is the Google Python library for doing machine learning stuff.
Yeah, I mean, so the second chapter that you will have in deep learning is basically just a 5 to 6 minutes video, and that video will tie
building
up
models.
I mean, see our first video, and then you can come over here, watch the second video from second lesson. That's basically what's going to tie up convolution to deep learning, or how we are using it in Keras or something. It talks about how you use different convolutional layers and how they affect how the machine is seeing those images, and now how to implement those layers and backpropagation and all those things. That's what we are going to start learning now on the third lesson.
Yeah, and so we're going into this TensorFlow programming lesson over here, and we're gonna move not into this tutorial part, but we'll actually go into the exercise. So if you click on that, then you can see there's the video and some sample code, and we're actually just gonna kind of skip by all that, and we're gonna use a powerful TensorFlow model yourself. I've already opened it. It takes a minute to open, so just went ahead and brought it. So now this is where programmers have a little bit of a sense of humor. So in order to get us going with convolutional neural networks, we're actually going to kind of rebuild a similar program to what was built in the TV show Silicon Valley. One of the characters builds an app called Seafood that really just identifies hot dog or not hot dog, and so that's the problem that we're going to try to solve is, are we seeing a hot dog or not a hot dog?
Oh, interesting.
Which if you do a good bit of software development and you've interacted with startup business culture at all, it is a really funny show.
Yeah.
Not appropriate, but
it is on HBO.
Yes, it is on HBO. All right. So first thing that you got to do is you got to import some libraries, and you got to know where your data is. So in this particular instance, the data is at this directory, input / hot dog, not hot dog. And so this is just telling our code where the image files are.
Yeah.
And then it looks like it's just it's just pulling in two images.
Yeah.
Is that what that looks like to you?
Yeah, for both hot dog and not hot dog.
Okay. So apparently we're just pulling in two images.
Yeah, and it looks like we are using a pre-trained model over here. So
we're not
actually
training
learning
anything. Yeah. We're not doing any machine learning. We're doing machine recall, I guess.
Yeah.
So let's run this cell. And I think that ran. Yeah. Okay, so it ran pretty fast because it's just updating some text fields.
Yeah, I mean, once you run this cell block, your image paths should have all those values. So It's pretty simple to understand. It's basically like the not hot dog image directory has this as its value, and not hot dog paths is basically just joining this location or the folder in which not hot dog images are there, and joining it with the file name. Your file name is either is first this and then this. So this list is going to have two elements.
Yeah. And then image paths equals hot dog paths plus not hot dog paths will give us four a list with 4 things in it. All right, so let's see. All right, so now what we're gonna do is, so we see this TensorFlow .keras library is being imported, and the learn tools being imported, and so we're going to run this cell here, because what it's going to do is first import the libraries, then we're going to specify what our image size should be, which is going to be 224 by 224. Now your images do not have to be square when you're doing convolutions and when you're doing deep learning, but it makes your life a lot easier to have them be square. Because basically anytime you do image transformations, you got to make sure that you're just keeping track of all the matrix math through, and it's easier to just do that once instead of twice and then potentially get them confused.
Yeah, and that is also useful in generalizing your entire image dataset. So like if you have one very grainy image and one very high definition image, then the high definition image in just a small pixel size that's equal to the pixel size that you have in the grainy image, it might not have all the details. By just downscaling those images, or you're making all of the images constant. That is also useful in when you are going to make predictions on some other images in your validation dataset, because your validation dataset could be anything. Like if I built a model with only 720p images, I don't know what it would be in this matrix form, but 1024 into 7 something. And if I push it out as a web app where you can feed me any image and I'm going to make a prediction based on the training data sets that I had, whether, like, let's just use this example, whether it's a hot dog or not. And you give me a complete DSLR photo of hot dog, and I was not using that at all in my training. Then there would be discrepancy. I would not make proper predictions. And then just downscaling your image so that it matches the 720p images that I used for training my model, that gives us the consistency, and I should be able to predict your images better.
Yeah, so that's all a good point. It is really important to just keep track of what your image sizes are and being consistent. And the more consistent you are, the better you should be able to predict, especially in kind of a general case. So this next function is then just pre-processing the images. Let's see, so it looks like it is loading each image into an array and then running them through this pre-process input function. The load image function will force it to be the 224 by 224. And the pre-process input, I believe, does some normalization of the brightness values in the images.
It seems like we are getting it from ResNet 50 or something. So
let's see. So then, we're creating a model, which is going to be ResNet 50, which is a well-published neural network architecture. It's got 50 layers. So one question you might have is, what's the difference between machine learning and deep learning, or neural networks and deep neural networks? And really it's just kind of a catchphrase buzzword for how complicated the models are. As a rule of thumb, if it's less than 7 layers, so generally when we're talking about deep learning, we're talking about neural networks, which are constructed of lots of little neurons in multiple layers. When you learn about neural networks, you do something called a perceptron, which is just like one layer of those nodes, or you might do a multi-layer perceptron, which is like 2 or 3 layers of those nodes.
Mm-hmm.
But then once you move to more than 3, then you're starting to get into the realm of deep learning.
Okay.
Because more than 3 layers is where it really starts to get difficult to train it quickly if you're using CPUs.
Okay.
And deep learning has only really been possible once we realized that we could do the matrix multiplications on GPUs, circa 2012 or so. And so I would say, as a general rule of thumb, once you're over 3 layers, then you're starting to talk about something that you could conceive as being deep learning. ResNet 50 has 50 layers, which is certainly deep compared to a multi-layer perceptron of 2 or 3 layers. All right. So this is not showing us our predictions, but I'm assuming we're going to look at those in a second, because it's running it through this myModel.predict, the test data, which is those 4 images that we pulled in. So let's look. All right. Okay, so let's see. So it's going to print the likely labels for the image and the image. So that looks like a hot dog, and yeah, it says that it's a hot dog first.
Yeah,
it might be a king crab.
King crab for 6%.
6%, or a cheeseburger for
0.6%. Pretty good. I thought it would be more confused between hot dog and a cheeseburger rather than a king crab.
Yeah, I'm not sure where the king crab comes from, but let's see.
Onion rings or hot dogs, actually. There is no onion rings. So
yeah, apparently they didn't train this network with onion rings. So that does a pretty good job with hot dog. All right, and then it's interesting because this just says that there's a plate in the image.
It is technically right, but that's not what we asked for.
Yeah, there's a plate, burrito next, and hot dog. It's really not sure whether it's a burrito or a hot dog. Let's see, some guacamole here.
All right, so
99%. That's guacamole.
Yeah, definitely.
All right, so now we get to actually do something.
All right,
so we're going to bring in the learning tools here, and we're going to write some functions. All right. We want to distinguish whether an image is a hot dog or not hot dog, but our model classify pictures into 1,000 different categories. Write a function that takes the model predictions and returns a list of true or false values in the same format as preds from the setup code. Okay. Work iteratively, figure out one line at a time outside the function, and print that line's output to make sure it's right. Once you have all the code you need, move it into the function is hot dog. Okay, so let's just see. Did I already? Oh, apparently I've already run through this in a previous effort. So basically what we're doing here is we're trying to write a function that just tells us, is this a hot dog or not a hot dog?
Mm-hmm.
because ResNet 50, the weights that we pulled in is where it's trained on ImageNet, which is actually looking at 1,000 different classes. So it's not just looking at hot dogs and not hot dogs, it's looking at hot dogs, cats, dogs, cars, airplanes, bicycles, whatever people decided to put in ImageNet. And apparently hot dog is one of the things that they decided to put in ImageNet. Along with guacamole and cheeseburger and plates. So then what we've got to do is we've got to pull in the predictions, and then basically we just loop through the predictions and look at the first prediction for each image, because that's the most confident prediction that we have. And if the very first prediction is hot dog, then we return, yes, it's a hot dog. And if it's not a hot dog, or true, and if it's not a hot dog, then we return false. So let's see what this next piece is. Exercise 2. So now we have a model. Is it good enough to build the app? Use the isHotDog function from above to help write your function. Alright, so let's see. Alright, so this paths to other images. This looks like this is pulled in from the Learn tools. Oh, my function did not return a value.
Return the accuracy.
Oh, calc accuracy. Oh, because it's just passing right now. So I didn't put this in here earlier. All right, so we want to use this somewhere here. Model, pass the hot dog images, pass the other images. And then this just returns
whether it's true or false. So
for each prediction. Okay. So let's see. So we've got to use it is hot dog model dot predict. Oh, we've got to also do this part, right? Oh, okay. All right. So this would be test hot dog. And we made this read and prep images earlier. Let's see. Do we want to put all of the images in one? I don't think so, right? Because we need to be able to have them separate.
Yeah.
Okay, so okay, and that function turns out, which is just true or false for each one, right?
Yeah.
Yeah, 4L labels. All right. Oh, let's see. Call that hot dog breads. Okay. And then we've got to make a second line here where we're going to read in our not hot dog images. So paths to other images. So test other data. All right. So now let's see. The accuracy. So basically, if we have the summation of all the hot dog predictions, so is sum a function? I think it is. So if we have the sum of that divided by the length of that, right? Let's see. So that would just be. Trying to remember. Okay, so accuracy, would that be the sum of all of the true positives
Accuracy would
divided by the sum of all the predictions?
Yeah, sum of all the labels.
So, so it would be the sum of hot dog preds, because each one there, or each true, is a true positive. So plus 1 minus other preds, because if it's false, that's a true prediction. So then all of that divided by all of that divided by the length of the one plus the length of the other. Is length? Oh, it's len. Length of hot dog breads plus len. So the length function is really helpful. It tells you how long the list is for an array. Okay. And we're going to return that. Let's just see if that works and it doesn't crash. It does not work. Unsupported operand minus O.
So what was the...
So I guess... Oh, let's see, we can do this another way, because it's basically just saying it doesn't like adding or subtracting 1 from predictions that should all be false. But if they should all be false, then the sum of that, let's see, the number of true predictions should be okay, it should be the length of that variable minus the sum of that variable. Yeah. Because basically this sum of that other prediction should be 0 if it's all a true prediction.
Yeah.
But if it's not 0, then that takes 1 away. So if I just take the length of that variable and subtract away the total number of trues,
Yeah.
because there shouldn't be any trues, then that should give me the accuracy. Let's give that a try. Okay, let's see, let's try to put this in a variable. Am I supposed to put a... No, does it work?
No, just return.
Okay, my function returned 0.5. Alright, so let's see. Let's print out the individual pieces here.
Alright,
What
so
are you thinking?
so the hint basically mentions just
What does the hint mention?
so hint actually mentions just using the hot dog dataset.
Really? Yeah, let's look at that hint. Make predictions for the hot dog images. See which are labeled as hot dogs and sum up the number correct.
Oh, okay. It needs the other images as well. Total of the number correct and divided by the total number of images.
Yeah. So
Test hot dog predictions is hot dog model dot predict.
yeah, so if we look at that.
How much does it give?
There's one up there, 0.75 for the bigger data set. And then if we do the same thing for the other predictions,
How about if we just do
this is where I'm messing it up. I'm not changing my data. That would have something to do with it.
Okay.
There we go. All right. So once again, if it's not working, look at the data.
Yeah.
I think that's what that's the moral of the story. So what I had done is I was making the prediction twice on the hot dog data, and I forgot to bring in the other data. All right. Now that we've got that working. All right, so now there are other models besides ResNet. Let's see.
DSJC-033.
DSJC-033. So let's bring in DSJC-033.
Yeah.
So we'll just type in DSJC-033 and bring in the weights. So it's important to realize that if you just specify DSJC-033, it will give you the architecture, but it won't give you the architecture pre-trained for any data set. So you really need a lot of data to get anything nice out of it. But if you use the pre-trained network, then it's already set up to give you some classifications. Okay, so we're going to do that, and then we're going to come up here and we're going to snag our accuracy function. Okay, we're going to change this to DSJC-16 model. Did that look right to you?
Yeah.
Apparently it's not. But I do.
Oh, wait.
Oh, it's weights, not weight. Okay. So yeah, so this is something I would expect. The ResNet 50 architecture is a little bit newer and a little bit more complicated. DSJC-16 is just basically extending the multi-layer perceptron model to just more and bigger layers.
Mm-hmm.
Whereas ResNet 50 has some like skip connections, and it's a little bit more complicated of an architecture. But it tends to perform a little bit better. All right, so that's everything for this example. Next time we'll talk about transfer learning. So here we didn't actually do any deep learning. We just used a pre-trained model.
Yeah. It was already pre-trained for us. We didn't have to wait for it to learn on test images.
Yeah, so if you see any of like the Microsoft or Google like be a deep learning or make a deep learning app without doing anything, this is basically what they're doing, is they're pulling in a pre-trained network and just applying it to your situation using something that everybody or has been previously tested that they know works really well for a broad variety of things, like recognizing objects or what have you, and then just allowing you to use their network weights. The transfer learning is the next step that sometimes they go to, where they allow you to take a bunch of pictures of a certain situation and then kind of tune the model for a particular situation. And that's what we'll look at next time.
Yeah, I mean, one good thing to take from this exercise is that how do you use your model after you have worked on it, after you have trained in it, everything. You can actually just export it out as an H5 image, H5, right?
Yeah, H5.
Yeah, H5 image, and then you can use it in some other programs. That's how, if you want to create a web app, in your Python you pre-train and everything and just push out or export out that H5 image.
Yeah.
And in your web development, whether you're using JavaScript or again you're using Python to build your web application, you can specify this H5 pre-trained model and just work through that, because you're not going to learn anything more since it's a pre-trained model. You're just going to use that pre-trained model to predict.
Yep. So yeah, that's it. Shoot us any questions that you guys might have, and yeah, we'll talk to you guys later.
All right.